Welcome to the second lab for day 20 of iste780 Data-Driven Knowledge Discovery. I'm Nick McQuaid, and this is a lab on clustering. I've already written the commands in from lab 2 of chapter 10, and I've started R. So let's get going here. First, we'll do k-means clustering. We'll set a seed so we get the same results as the textbook. And we'll create some data. Now this is fake data, and we've stretched some of it out in either 50 observations, or no, what is it? Yeah, 50 observations. We've stretched some of it out in one direction, stretched some of it out in the other direction. So we know that there are going to appear to be two groups, but we're going to cluster as if we have two groups. Here's the clustering model. We've got, something like half of them in group 1 and half of them in group 2. And here's a plot of them. And as usual, the plot's off the screen, so let's do this. And you can see that the groups are well separated. Let's see. Yeah. Don't think there's anything unusual here. This is the plotting character. This is character expansion size. CEX equals 2 made these dots quite large. The plotting character 20 is the dot. The default plotting character that we use a lot is plotting character number 1, which is the open circle. Okay, now let's pretend we don't know there are two clusters. I'm going to set the seed again, and we're going to try 3 clusters. Remember that in k-means clustering we have to decide how many, we have to decide in advance how many clusters we believe there are. By the way, I don't know, actually, I'm not sure if the textbook has this here, but here the textbook has n start equals 20, so this causes us to have a number of initial configurations to go from. So let's take a look at this. So here's the output of that one, and there are a few in each cluster. Let's take a look at it visually. So basically what's happened is the one cluster's been split into 2. Okay, now let's take a look at the usefulness of the n start equals 20 parameter. That has us, that if you recall, I've mentioned that k-means is a greedy algorithm. It can be trapped in local optima. So starting from different initial places can be extremely useful. So here we're going to do it, we're just going to start in one place, and then we're going to take a look at the within cluster sum of squares, and we get the within cluster sum of squares is about 104. And recall, this is what we want to minimize. Now we'll try it with 3 clusters with n start equals 20, so we have 20 initial configurations, and the best within cluster sum of squares that we get there is better. So it's crazy to do this without, it's crazy to just use the default here, n start equals 1. You should certainly use, the textbook advises n start of 20 to 50. Okay, and that's it for our k-means clustering. Now let's take a look at hierarchical clustering. So, and we're going to, if you recall, we have one of the choices that we have to make is the kind of linkage of the clusters, and complete linkage causes us to measure the clusters. The distance between 2 clusters is the distance between the 2 points in those clusters that are farthest from each other. Farthest, the point in one cluster that's farthest from the farthest point in the other cluster. And we're going to do all 3 linkage types. So average linkage and single linkage does what's closest. And this is going to look, okay, so we're going to do the dendrogram. We're going to display the dendrograms, and let's just take a look at those. So here's the one for complete linkage. I've done one parameter that's not in the textbook, which is I've made the plotting characters much smaller than the textbook to give you a fighting chance of being able to see them. That's what this. Oh no, actually here I just left it the size of the textbook. Let me. All right, I'll leave it the size of the textbook for now. What can I say? At least this way I'll have all three of them be the same. Okay, and you can see as before we have very different pictures of one. These two are obviously balanced. This one is extremely lopsided, and this is the same kind of situation we saw in the textbook examples. Now let's cut the trees, and that means we're going to find out how many items are in each cluster. So here we've got a fairly even number of items in the two clusters. Here again we've got a fairly even number of items. And here we have a much worse situation. All the items are in one cluster except for one. There's a single item in cluster number 2. So let's try this into a different level. Try cutting at a different level to get a better picture. I think what we had was observation 16 was in another cluster, and then everything else is in one cluster. Whereas the tops of these are the tops of 2 bushy trees. Okay, and so when we did that, we now have 3 or 4 clusters. We have a couple of, here's a, number 4 only has one item, number 2 still only has one item, but 1 and 3 are somewhat evenly divided. Okay, now we should always scale the variables before we do hierarchical clustering, so let's do that. And let's do a hierarchical clustering plot. Oh, here I made the characters smaller than in the book. They were hard to see. I found them hard to see. And now let's compare this, which is Euclidean distance, which is the standard thing to do, with correlation-based distance, which we talked about and saw an example of in the textbook. So here we've just taken the correlation and used the asdist function on it to make it be interpreted as a distance. And these are both complete, right? Yeah, these are both complete. These headings are terrible. You'd have to expand this or make the headings smaller to make them look good. But in any event, you can see that the correlation-based distance is quite different from the gives us quite a different view from the Euclidean distance. And that's it for the clustering lab. Now we have one more lab to go, which is an application lab, and so I'll look forward to you joining me for that one. For the time being, let me just say thank you for your attention.